Hello students, welcome back to PH107 Quantum Physics and Application. Today I am going to discuss about Compton effect. So before I go and explain what is Compton effect and why it is so important in quantum physics, uh, let's recap what we have learned so far and what are the recommended readings for this particular topic. So if you would like to read more about Compton effect, you could go to section 3.5, page 86 in this Modern Physics by Survey and Co. Authors. So what we have learned so far, so in the past lectures, I hope you are convinced that light behaves like a particle, and we have got the notion of photons, and these photons have discrete energies in units of h nu, and once you invoke the particle nature of light and say that this photon has a discrete energy in terms of h nu, then you are able to explain black body radiation as well as photoelectric effect successfully. So till now we have talked about the energy of the particle photon. Now you know from your previous experiences that once you say that something is a particle, it means that this particle must possess some energy as well as momentum. So what about the momentum of the photon? The concept of the photon, the concept of the photon of the concept of the momentum of the photon did not successfully realized until Compton effect. So Arthur Compton in 1923 with Peter Debye, they performed an experiment, and in that experiment the X-ray photon is scattered from the electrons, and when they try to explain this experiment or the findings of this experiment, they concluded successfully that photon has a momentum, and I will discuss how it comes and what its value and all other properties. So let's see what is the Compton effect at all. So here is X-ray source. I will explain you at the end of this lecture why you need X-ray and not any other wavelength of electromagnetic radiation or light, for example visible light or infrared, and why X-ray is so important or peculiar. And here is a kind of monochromator which takes a particular wavelength. So here is your light. Now this light hits or interact with the target. Once it interacts with the target, the light is scattered up and it is collected in the detector. So detector collects the intensity of the scattered light, and here is the angle theta at which the light is scattered. And if you see the observation that Compton has made, that if the angle theta is 0, you see a peak of the scattered intensity at the same wavelength what the wavelength he is providing to the X-ray. But as soon as you start changing the value of theta from 0 to some finite value like 45 degree, you see that you start seeing a secondary peak, and as the value of theta increases more, that means at 90 degree, you see this peak is getting more prominent, and it's getting more prominent. Moreover, the distance between the primary peak at lambda and the secondary peak at lambda prime start separating more. So the distance between the two peaks increases as a function of theta, and the secondary peak become more prominent as the angle increases. So this was a very surprising observation that Compton has made when he scattered the X-rays from the target. So let's point out what are the exact constituents of the experiment and what are the assumptions one could safely make. So Compton illuminated graphite with X-ray. So the target was graphite. He observed that the scattered radiation has a longer wavelength, that is a lambda prime, than the incident radiation or incident X-ray, that is at wavelength lambda. On the grounds of the wave theory, it is impossible to explain why the wavelength is changing and why we are seeing the two peaks at different wavelengths. Now, When you talk about the graphite, there is an abundance of weakly bound electrons, so it is safe to assume that these electrons, or these weakly bound electrons, are equivalent to the free electrons. Now when the photon interacts with the graphite, or the free electrons of graphite, it exchanges some energy, and the X-ray after the interaction flies away from the uh, uh, system, it means graphite, with less energy. Okay, so the energy is reduced once the X-ray is scattered and reached to the detector. Now we know that energy must be conserved, so the remaining part of the energy is the kinetic energy that the scattered electron take, and now the electron is also in motion. Initially it was in rest, and now it is also in motion, so it also flies away in some other direction. So now what comes out up from this study, that scattering of light by electron can be treated like a collision between particles, which further substantiate the particle nature of light. And that is the important lesson that we have learned in our previous lecture, that light is behaving like a particle, and these particles are called as a photon. So let's look the collision between X-ray photon and an electron which is at rest. So this is the schematic I have shown you, and now this is my X-ray. So you know what is the energy of your radiation, that is h nu, and now this is the target which is at rest. So here it's a free electron, and now the X-ray reached to the detector with longer wavelength, so less energy. So let's apply energy conservation. So what is the energy conservation? So here is the before the collision, this is the energy of your photon, this is the energy of your electron at rest, this is the energy of your photon after the interaction. So this is the energy of your scattered photon, and this is the energy of your electron after the collision. So this is the total energy after the collision, this is the total energy before the collision. Now if you want to write down this expression in terms of the wavelength, so I can easily write down this h nu is equal to sc by lambda, and here also I could write down h nu prime is equal to sc over lambda prime. And now there are two problems. By looking this equation, there is no way that we can connect the relation between lambda and lambda prime immediately or straightforward. The other problem is that what is the energy of an electron which is at rest? What is the rest energy of an electron? This is another problem that we have. So by looking this equation, we are not able to explain the observation that we have seen, that there are two wavelengths, and what is the relation between the two wavelengths, and how the separation between the two wavelengths depends on the angle theta. So let's apply another conservation that we know, because both photons and the electrons are treated like a particle. So we can also apply a conservation of momentum. So the electron is at rest, so there is no momentum, only photon is moving, so photon has momentum. So this is the total momentum before the collision, and this is the total momentum of the system after the collision. So this is the momentum of your photon, and now P is your momentum of the electron. Now here is another question, that what is the momentum of a photon? So to answer these two questions, what is the momentum of your photon and what is the energy or the rest energy of an electron, we have to recap some of the important concepts of physics, which is the special relativity. So what is special relativity does for us? It modifies our notion of energy and momentum. That's what we have seen in our previous slide. So let's say you have an object which has intrinsic mass, or now we can call as a rest mass m0. So then we can easily say at the relativity, special relativity says to us that this object has rest mass energy, which is A is equal to m0 c square. And this expression I'm sure you have seen or you have heard in the past. Now let's say this mass, if the mass is in motion with velocity v, then the relation between the rest mass and the actual mass is in this following way, where mass m is written as m0, which is rest mass, divided by 1 square root of 1 minus v square over c square, and this quantity 1 over square root of 1 minus v square over c square we write as a gamma. Okay, so now once we know the momentum, once we know the mass, we can easily write down the momentum. We know the momentum is mass time velocity. So here is mass is your gamma m naught. So I have written gamma m naught times velocity. So this is what we have seen in the previous slide. So now what I can do some mathematical simplification. So now I can take this part toward this side. So what I will see, m times square root of 1 minus v square c square is equal to m0. Now I can take the square from both sides. So once I will get m square, and then square root is gone. So I will get 1 minus v square over c square, and this side I will get m0 square. Now I can take this m square inside this bracket. So what I will get first m square, then I will get m square v square over c square. Now what I can do, I can multiply this whole quantity left hand side and right hand side by the c to the power 4. So first what I will get, m0 square times c to the power 4, and here what I will get m square times c to the power 4 minus m square v square c to the power 4 divided by c square. So total I will get c square. Now this thing I can write down mc square power square, and this quantity I know from my previous slide that mv is momentum, so this is a momentum square. So now in a very simplified way I can write down m0 square c to the power 4 is equal to, this is my E, so E square minus P square C square. So now what I have got, that E square is equal to m0 square c to the power 4 plus P square C square. So now if, let's say for a case of photon which has rest mass 0, then what is the energy? Energy E square is equal to P square C square, or E is equal to PC. And for the electron which is at rest, so momentum is 0, then it has only rest mass energy, E is equal to m0 c square. This is what we have seen in the previous slide. So what we have concluded till now, that the energy of an object with this momentum within this special relativity is E is equal to square root of P square C square plus m0 square c to the power 4, and if the particle has rest mass 0, which is the case of photon, then the total energy is Pc. And we know that the energy of your photon is also h nu. That's what the hypothesis that Planck and Einstein have put forward. So if we equate the two equations, then what we can see, that Pc is equal to h nu. Now P is equal to h nu by c, and we know that how the frequency and wavelength are related. So I can write down the momentum is equal to h over lambda, and this is how we have got the momentum of a photon in terms of wavelength. So this is what we have seen in the previous slide. Now momentum is a vector quantity. So now I can write down the modulus of this momentum as a magnitude is equal to h cross. So what I have done, I have taken h by lambda and I have multiplied 2 pi here and I have divided by 2 pi here. So h over 2 pi is known as h cross. So that's why I have written 2 pi h cross over lambda, and we know that 2 pi over lambda is your wave vector. So that momentum is related to the wave vector of a photon, and this wave vector has a direction and it has a magnitude which is 2 pi over lambda. That's what I have seen. So this conclusion Einstein already made in 1906 when he was studying a molecular gas in thermal equilibrium and how these are interacting with the electromagnetic radiation. But the only validation came when Compton did the experiment, and to explain the observation that Compton has made, this notion has been invoked, and this notion has been successfully employed to explain the Compton's observations. This is what you have also seen briefly in your 10+2 in 11th and 12th standard, or in your previous study. So this is the chapter 11, dual nature of radiation and matter, and if I quote that all photons of light of a particular frequency or a wavelength have the same energy h nu or a c over lambda, and momentum P is equal to h over lambda or h nu by c. So this you have already seen, but in this lecture what I have shown you that this equation or this concept arises from the special theory of relativity. Now Another thing that you have seen in this chapter, that in a photon particle collision, that's what we are trying to understand, that a photon interacts with an electron, such as photon electron collision, the total energy and total momentum are conserved. Okay, that's what we are going to employ. So let's look back this schematic. So here is your incident photon with energy E and momentum P. Here is your electron at rest. After the interaction, the electron flies away along this direction. This is the recoiling electron with energy PE and momentum with energy EE and momentum PE. And this is the scattered photon with energy E prime. And this E prime must be smaller than the original energy E, because some energy it has given to the electron, and momentum P prime. So the total energy and the momentum for the electron E square is equal to P square C square plus M0 square C to the power 4. That's what we have seen. And this is the momentum. And for the photon, E photon is h nu, and the momentum of photon is h nu over C. So this is what we have seen. So first let's employ the conservation of energy. So we have seen before the collision, h nu is the energy of photon, m0 c square is the energy of your electron at rest. So this is the total energy before the collision. This is the total energy after the collision. H nu prime plus E is the energy of your recoiling electron. Now let's apply the conservation of momentum. Now this electron is flying away along this photon is flying away in this. So now the total momentum has two components. So let's first write the conservation of momentum along the x. So this is the momentum along x. We have to project this one, and we have to project this momentum. So before the collision, only the momentum of the photon, that is h nu by c. After the collision, this momentum is p prime. So I can write down h nu prime by c and the cosine component or the x component cos theta, and the same applies to this recoiling electron. So pe cos phi, because this angle is phi and this angle is theta. And similarly we can write down the y component. So y component, there is no y component in the initial, okay, so there is zero component here. Now the y component for the electron will be along this direction, and y component for the photon along will be this direction. Both are going to be minus. So I can write down h nu prime by c sine theta is equal to pe sine phi. So these are the x and y component of your momentum. So this is what I have told in the previous slide. So now what the thing first we can do is try to eliminate the cos phi or sine phi. So let's eliminate the phi variable. So let's square it and add it. So here I have squared it. So p square cosine square phi plus p square sine square phi. So this is quantity 1. And here what you have got, I have transferred this quantity along this side. So h nu divided by c minus h nu prime divided by c cosine theta whole square plus h nu prime divided by c sine theta whole square. So this is what you have got it. Okay. So now if you expand this quantity, what you will get? You will get h square or h nu by c whole square plus h nu primes divided by c cos theta whole square. Then you will get 2 times h nu by c h nu prime by c cos theta. And when the cos square theta and sine square theta are put together, they will give you 1, and it will only give you h nu by c whole square. So that's what you have got. So this is the momentum of your electron. This is the energy conservation that we have seen. And I can write down the energy EE by taking this quantity towards the left. So h nu minus h nu prime plus m0 c square. This is the energy of your electron after the collision. Okay, but we know the relativistic energy from our previous slides can also be written in this following fashion. And we have also seen from the previous slide that this is the momentum of the electron. So what I can do, I can substitute this value of pe square here. Okay, so what I will get, the first time I will get h nu divided by c whole square times c square. So c will cancel out. So I will get only h nu whole square. The same is applied here. So h nu prime divided by c whole square multiplied by c square. So c square will cancel it out. So you will get this. Then again the c square will cancel it out. So you will get 2 times h nu prime cos theta, and then you will get this rest mass energy term. Okay. Now this is the total energy square. So I can also make a total energy square here. So h nu minus h nu prime plus m0c whole square. So now in left hand side I have E square, and right hand side I have two different quantities, so I can equate. So let's equate these two quantities. So what you will get, when you expand this square, you are going to get 6 terms. So first term, h nu whole square plus h nu prime whole square plus m0c square whole square plus 2 times h nu prime minus, then minus 2 times h nu prime m0c square, okay, then plus 2 times h nu m0c square. So this is what you have got it from this one, and this is what you have got it from this one. So if you equate this quantity, the first term will drop out, the second term will be cancelled out, okay, and this quantity will also be cancelled out. So what you have got at the end in this equation is this quantity minus 2 times h nu prime cosine theta, and here you have got this quantity, okay, and you have got other quantity that we can take it out here. So we can take m0c square out 2 times, and then we can say h nu and h nu prime in minus sign, okay. So this is what I told you, that this is what we have got it, okay. So if you simplify by yourself, you see that h nu minus h nu prime times m0c square, this is coming out from this equation, and this is coming out from this equation, and I have taken this 2 times h nu prime along this one, so I can write down 1 minus cosine theta, and 2 get cancelled out. So this is what I have got it. Now I can write down this frequency in terms of the wavelength. So this is what I have written down in terms of the wavelength, okay. Now if you take this hc from this side and hc from this side, it will be cancel it out, okay. So what you have got at the end of the day, if you simplify the whole thing, you have got lambda prime minus lambda, or you can say now delta lambda is equal to h divided by m0 c 1 minus cos theta. So this is what you have obtained after employing the conservation of energy and conservation of momentum between photon and an electron, and the photon momentum and the rest mass energy of an electron arises from the special theory of relativity. Now I can define this prefactor h over m0c as a Compton wavelength, and if you substitute these values, you will see that the Compton wavelength comes out to be 2.43 into 10 to the power minus 3 nanometer. The another important thing is that this Compton wavelength is independent of the wavelength of the radiation that you are assigning to the matter, either it X-ray or in the visible region or infrared region or UV region, but this depends on the mass of the scatterer. So whether you are scattering from the electron, or you are scattering from the neutron, or you are scattering from the proton, accordingly this Compton wavelength will change. Now here I have provided you this value of Compton wavelength in different units, which are sometimes useful when you want to convert from meter to electron volt second, or in terms of other values. So it's useful to know how these are converted from one unit system to another unit system. So this is what we have got. The difference between the scattered, shifted and unshifted wavelength, or lambda prime minus lambda, is written in terms of the 1 minus cosine theta times the Compton wavelength. So here is again systematic. So your X-ray is coming out from your X-ray tube. Here is your carbon target, and this is the some arrangement by which you are collecting the scattered photon in the detector. So at 0 degree you have only unshifted peak, and once you move from 0 to 45 degree, you start seeing as additional peak. And as I told you in the earlier slides, that as you increase the angle 90 degree, you see this peak more prominent, and the difference between the shifted and unshifted peaks increases. So the shift in the wavelength is 0. If you substitute theta is equal to 0, then cosine theta will be 1. So 1 minus 1 is 0. So that's why there is no shift in the wavelength. And if you substitute theta is equal to 180 degree, so that means 1 minus minus 1 means 2, then you will get 2 times Compton wavelength. So maximum shift you are going to get when theta is equal to 180 degrees. So the shift increases from theta is equal to 0 to theta is equal to 180 degree, and that's what you have seen here. So no shift appears and the shift increases as the angle is increases. Okay. Now here is a quiz for you. So why do we see a non-shifted peak at all angles? Okay, this is a question that you have to answer. That's what I have shown you, or what Compton has made an observation, that you see an upshifted peak all the time along with the shifted peaks, depends on the angle of your observation. So this is the Compton wavelength. This is what I have told you. And now here is the explanation why you need X-ray to see the Compton effect or Compton observation and not UV or visual light. So you have seen that the maximum change in wavelength, which is 2 times lambda c, is of the order of 10 to the power minus 12 meter. This is insignificant for a visual light, which is 10 to the power minus 7 meter, which are 800 nanometer or 400 nanometer, but not for X-ray or gamma rays, which are of the order of 10 to the power minus 10 meter or smaller than that. Okay. Now this equation, what we have achieved in today's lecture, is valid even if we have particles other than electrons which interact with the photon, and the photon is scattering from that particle. The only important thing is that you have to choose the value of this rest mass accordingly, whatever the particle from which the photon is scattering. So what is the take-home message for today's lecture? Photon, just like any other particles, carries energy h nu and momentum h over lambda. The success of photon story or photon theory in explaining interaction of light and electron consists the classical contrast the classical or wave theory of light. So this is what is the important lesson that we have learned in this lecture and the last lecture, that the success of photon theory in explaining interaction of light with electrons is in contradiction with the earlier notion, which is the wave theory or the classical theory of light. So now it leaves us with the dilemma whether light is a particle or a wave. So light has both wave and particle properties. Depends on what you are going to measure, and what you are going to see depends on the way you are going to explain one of the property you need to invoke. Thank you very much, and see you in the next class.